Awesome. Thanks, Jean-Marc. Let me share my screen real quick. Can you guys see this?
Yeah, good to go.
Awesome.
Yeah.
That intro was too kind. I feel like I have large expectations to live up to. I think most of those things are an overstatement to some degree, but I will concede that I am a recovering academic in many senses. So spent some time in undergrad at Harvard studying adversarial robustness, adversarial attacks of AI systems, and evals. And ultimately, I was really planning to start a PhD. I was supposed to go to Stanford for a PhD last fall, but I think there were so many real-world robustness issues that we ended up commercializing Haize, and it's been a blast ever since. What I'm going to talk about today is one specific aspect of robustness, which is judging the output of AI applications through scaling judge time compute is what we call it, and specifically with our library, Verdict. So a little bit more background on Haize itself. So what does Haize actually mean? Haize is all about rigorously testing AI systems so that you can build trust that they actually work and perform exactly as you intend them to, right? You can think of Haize as basically fuzz testing or being a DAST for the Gen AI era. Haize is probably best known for applying our approach and testing to red team all of the frontier labs like Anthropic and OpenAI and AI21, and also working with great companies on the app layer like Deloitte and others you can see here. We've assembled really a world-class team in service of this mission. PhDs, PhD dropouts, ex-founders, CTOs from YC and others, ex-quants. And then really we've got a great advisory board from people in the traditional security world, so former CISOs at all these tech companies, professors that lead AI safety research, and then of course, AI policy and responsible AI directors at large companies. And then worth briefly mentioning that we raised some money from great angels and then General Catalyst. Cool. So I want to talk about what it is I really mean when I say AI robustness and why it matters, right? So if you're familiar with how people have done AI evaluations for the past, half century or so, it's really been centered around creating a golden data set of static inputs and outputs, sending the inputs and outputs to your AI application, and then sort of measuring things somehow between the generated output and the expected output. This doesn't quite work for Gen AI land, specifically because Gen AI apps are extremely brittle. And I mean brittle in this very particular sense, which is when you send two similar looking inputs to your AI application, you may get wildly different outputs on the other side, right? And technically, I would call this AI being Lipschitz incontinuous, but all this really means is AI is extremely sensitive and fickle and brittle vis-a-vis the input. And this, of course, leads to a lot of real-world manifestations of harm and legal and brand and reputation damage. So Air Canada chatbot hallucinating a free discount, Chevy pickup truck $1, you can buy it off of their dealer website, character AI telling a teenager to commit suicide, plenty of examples of this real-world manifestation of brittleness. And broadly, we refer to this as the last mile problem of building an AI, right? It's super easy to spin up something in Gen AI land that is really sexy for a demo ready, Twitter ready, whatever you want to call it. But it's much harder to get that same application out into production, into a real use case, something that's enterprise ready. And we call that huge chasm the last mile. Okay, so how does Haize go about actually solving this last mile problem? We do this broadly by simulating the last mile, right? Sort of being like a DAST or fuzz testing for AI applications again, right? And what this concretely means is we will try and synthetically generate inputs that are from a representative user distribution. We'll send them to your AI application. We'll get the response from your AI application, and then we will judge, which means we will automatically analyze the output of your AI app, the response from your AI application, to see if there's some sort of anomaly or unexpected behavior or otherwise undesired quality from your AI app. And we do this in an iterative process, right? So based on our analysis of the response, we'll figure out, okay, should we exploit this specific area in which your AI application is weak? Should we fan out and try and be a little bit more diverse and explore, right? And we'll do this iteratively until we uncover corner cases and bugs and vulnerabilities. So we think basically, technically about both sides of this equation, which is one, how do we simulate faithful, diverse, difficult, and complex inputs? But equally important is how do we actually judge and do an analysis on the output of your AI application, right? And this is particularly difficult in the Gen AI era because the output of your your AI app is totally freeform, right? It's unstructured, it's messy, it's just raw text, and it's very, very variant in terms of what it can be. And so if you think about really what you would desire as a gold standard is just to have a human subject matter expert oversee your AI application and tell you whether or not that response is good or bad, right? That would be the gold standard. But of course, this is inadmissible and intractable in practice. And so our goal is to figure out how can we essentially take that human subject matter expert and then clone it into what we call a judge model, right? There are a couple ways that you can do this, right? You could try and train your own LLM judge. You could just use a off-the-shelf third-party reasoning model or API from OpenAI or from Anthropic or whatever have you. But all of those issues, all of those approaches have their own issues. And we take a very different approach, a prescriptive approach that we call scaling judge time compute, right? So we're familiar with pre-training scaling laws, inference time scaling laws, right? That's sort of been the crux of progress in AI over the past 5 years or so. We sort of take the same idea of increasing compute, increasing the actual number of tokens that you're processing, and we apply this specifically to the task of judging, right? Specifically to that task of verifying whether or not the output of your AI application is good or bad, right? And we released this library called Verdict about a month and a half ago at this point, basically allowing users to compose arbitrarily complex and scalable architectures of judge systems, right? And the key insight that we have here is, why is this different from a regular agent framework? Why is this different from a regular like LangChain-esque thing? The key point I want to point out is here. We borrowed a lot of insights and research ideas from the scalable oversight community. Scalable oversight being the practice of AI safety, trying to monitor complex and sophisticated AI systems to see if they're misbehaving and deceiving humans, right? So basically, how do you oversee that complex system to make sure it's not going to mess with your greater infrastructure and so on, right? We took a lot of those insights, in particular in our building blocks, right? So scalable oversight has a lot of great ideas about how you should, for example, debate amongst an LLM panel, or say self-verify or self-critique, or say fan out into an ensemble of judges and then prune down the results of those judges. There's a lot of these primitives that worked really well for the scalable oversight task that worked equally well for judging LLM outputs, right? And so Verdict is built around these building blocks. Also worth noting is that you can compose these building blocks arbitrarily with arbitrary complexity and fully with type safe guarantees, right? And so specifically what I mean by this is Verdict is a fully declarative framework. You specify the input interface to any sort of units in the Verdict pipeline. You specify the output schema of that same unit. And we basically guarantee that as long as you hook up any units directly together, that there will always be verification of the input and output schema, right? So this allows you to very, very easily scale up the number of LLM calls that you're making as part of this Verdict system. And concretely, we sort of see this as a PyTorch-like way of composing different LLM calls, right? You can do this intra-layer, and you can do this inter-layer. Here's a couple of examples of how you might hook up these different units together. And long story short, this allows you to build really, really powerful judging systems. As a couple of examples of how easy it is to actually specify a Verdict pipeline, you can see here in around 10 lines of code, or I guess really there's only 8 lines of code plus 1 line of code for visualizing the actual pipeline. You can really quickly build up this 5 LLM call system where you have 2 judges score an output of an LLM response. You have 2 more judges verify the initial scoring to make sure that it actually is correct or is consistent in its reasoning for whatever result it produced. And then finally, we can map down the results to basically pick the judge that has the highest post hoc verification score, right? And normally, if you were to do this, this is like at least, call it conservatively, at least 50 lines of code to orchestrate this entire thing, right? But in Verdict, it's just 8 lines of code. Again, because we've chosen these primitives so tightly. And as another example, we can sort of take that same initial pipeline that we defined on the earlier slide and then compose that arbitrarily with more and more layers of complexity, right? So you can see here, each of these individual components is the same, right? The same direct score judge map, sum module that we defined on the earlier slide. But we can compose all those together in ensemble and have them crosstalk to each other and then produce a final result, right? And that's just one extra line of code. We specify an additional layer with three repetitions of the same previous jury, and we get the results, we mean variance pool, and then aggregate all the final predictions down at the very bottom. So point is, this is why I say it's easy to build complex pipelines. You sort of just do it arbitrarily as you'd like, and we'll take care of all the type checking for you. But why does this matter, right? So this is all very cool from an engineering perspective, and it's just nice to build these complex systems. But as it turns out, verdict judges are just really freaking good, right? In fact, so we can beat the best reasoning models on verification and eval tasks, right? So specifically, when comparing here, expert QA, which is domain-specific fact-checking, and also excess tests, which is a safety task of content moderation, but only on difficult and borderline examples. And here we're beating O1 and O3 mini and other really powerful and frontier reasoning models with verdicts, and in particular, just using GPT-4o as the baseline model, right? So on expert QA, in particular, we're more than 10% better than O1, which is the next highest scoring model. And the other regular models like 3.5 Sonnet and 4.0 are far, far below that as well. And similar is true for excess test. And not only can we beat the best reasoning models in terms of performance, we can also do it on a budget, right? Specifically a price and latency budget. So here's a very simple graph. On the y-axis is accuracy in expert QA, and on the x-axis is the latency. The size of each dot represents the price, the actual cost of doing a single LLM call, or sorry, performing a single experiment across expert QA. And as you can see, verdict is up here, both extremely accurate and also extremely low latency for a relatively modest price vis-a-vis O1, which is like 3 times more expensive, right? And similarly, we beat out O3 mini by several points as well. It's a little bit more expensive, but of course, we're also beating it by 15%, right? And down here, you got GPT-4o and 3.5 Sonnet and other LLMs. Point is, you can get Soda on a really nice price and latency budget. And we're already starting to see lots of great adoption, both from the research community, but also from commercial entities, right? So Vogent is this really great voice agent company that launched officially on YC a couple of weeks ago. And they use Haize Labs' verdicts system to essentially perform line-by-line evals for all the customers that are calling their voice agent, right? And they use that as actually a means to self-improve and patch up errors that arise in their system, right? So you can see down here in the screenshot to the right, how they're actually surfacing the failures. And all these surfacing of failures are powered by verdicts. I do want to point out that verdicts is not really just about quote unquote evaluations in the offline sense of evals, right? So, you don't really just want to run verdict anytime you want to do like an offline test of your AI system. We actually see that verdict can be used both for evals as well as runtime guardrails, right? So monitoring your system out in the wild, and very interestingly, for test time compute, so acting as a verifier, as a reward model during test time compute, is helping you prune the actual tokens and actual answers that you're generating from an underlying model, and also as a reward model in reinforcement learning, right? In fact, we've trained using verdict as a reward really great jailbreak models that are several orders of magnitude smaller than the frontier lab reasoning models, but gets really, really strong performance, right? But the key point I want to make here is that verdict essentially allows you to perform reasoning and qualify reasoning in non-verifiable domains, right? And this is an extremely powerful tool to have in your toolkit, right? So instead of just having the ability to learn something when you have an exact ground truth answer, you can just throw on verdict to give you a very soft reward in terms of if you're directionally correct or not in terms of your reasoning. And I think this is broadly where the field is headed. Awesome. So I know we're basically at time. Verdict is still in its early days in many senses, but if you guys want to check it out, we got a lot of great open source contributors, including Omar, who is the DSPy founder and contributor, or DSPy inventor, I should say. If you want to scan the QR code, that's a link to our website. And then, of course, the verdict link is just right there.